Welcome to my differential equations final exam review problems and solutions video. This is going to be a pretty long video with a lot of pretty heavy-duty problems related to Laplace transforms, Hamiltonian systems, gradient systems, nonlinear systems, even a tiny bit with partial differential equations, as well as some theoretical problems related to trapping regions and unstable equilibrium points. Let's get started. You can see the first problem is a differential equation that's first order, and the right-hand side involves u5t, that's called the Heaviside or unit step function, with jump discontinuity at t equals 5. u5 of t has a value of 0 when t is less than 5 and has a value of 1 when t is greater than or equal to 5. Find the solution of this initial value problem, show all your work. All right, we're going to go through the Laplace transform method here to solve this. This is what you want to use. I'm not going to fully explain things. I'm assuming you've done this before and you just need some practice. There are going to be various kinds of properties that you need to help you solve this as quickly as possible. First, you take the Laplace transform of both sides of this equation. We can write L of the left-hand side, I'll just draw an arrow like that, equals L of the right-hand side, u5t. Then I can use something called linearity of the Laplace transform operator as a linear transformation to say that the Laplace transform of this linear combination of dy dt and y, the unknown function y of t, is the corresponding linear combination with the same coefficients in front 1 and 3. So it's L of dy dt plus 3 times L of y. That's what the left-hand side simplifies to after applying linearity. What about the right-hand side? What is L of u5t? That's something that you should either memorize or have on a formula sheet. That's going to be e to the negative 5s over s, where s is going to be the variable for the Laplace transform. That's just something to memorize. In general, the Laplace transform of ua of t, where a is a constant, is e to the negative as over s, technically speaking only when s is positive, but it's not something to worry about. We also need to know how the Laplace transform affects derivatives. L of dy dt, it turns out you can prove, is s times L of y minus y of 0. And there's where your initial condition is going to come into play. We're going to ultimately subtract 2 right there. Now what do? This is now an algebraic equation in the unknown expression L of y. We can just use plain algebra to solve for L of y, and then maybe, just maybe, we can then apply the inverse Laplace transform function to find little y as a function of time t to solve the initial value problem. That is the goal. That's the way we do it. First, add 2 to both sides of this equation, and then you've got 2 factors that involve L of y here and here. You can factor it out to write s plus 3 times L of y equals 2 plus e to the negative 5s over s. Now divide both sides by s plus 3. We can say the Laplace transform of the unknown solution function y, which is a function of time, is 2 over s plus 3 plus e to the negative 5s over the product of s and s plus 3. All right, we need some other facts. Some other facts you should either, again, memorize about Laplace transforms or have on your formula sheet. One key fact that we need is that the Laplace transform of e to the at power, where a is a constant, is 1 over s minus a, technically when s is bigger than a, but again, you don't have to worry about that. Notice also that if a is 0, this implies that the Laplace transform of the constant function 1 is 1 over s minus 0, which is just 1 over s. That'll be helpful as well. One other property that we need is how the Laplace transform is related to the unit step function, ua of t, times a general function evaluated at t minus a. Here's what I mean. What's L of ua of t, where again, this is the unit step function where the jump discontinuity occurs at t equals a, times little f, say, of t minus a. What does this equal? It turns out to equal e to the negative as power times capital F of s, where capital F of s is the Laplace transform not of f of t minus a, but instead of f of t. We're going to need these facts to help us essentially go backwards to apply the inverse Laplace transform, because what this would say is that the inverse Laplace transform of 1 over s minus a is e to the at, and the inverse Laplace transform of something like this is this expression, ua of t times little f of t minus a. That's how we're going to use these properties. We can use this first one, as well as linearity of the inverse Laplace transform, to say that the inverse Laplace transform of 2 over s plus 3 equals 2 times e to the at, where what's a? If you match these up, the a would have to be negative 3. And yes, the inverse Laplace transform is linear, so the inverse Laplace transform of all this is 2 times the inverse Laplace transform of 1 over s plus 3 plus the inverse Laplace transform of this expression, and I'll write it as e to the negative 5s times 1 over s times s plus 3. Again, this one can be computed just from this fact. This one can be computed from this fact over here, but it's a little tricky. You got to be careful. So 2 times this inverse Laplace transform by this fact right here, where a is taken to be negative 3, is going to be 2 times e to the negative 3t. But what about this part right there? How do I use this fact? It's not so clear what to do with this expression. What you do is something you do in calculus 2. You use partial fractions. We want to take 1 over s times s plus 3 and write it as some constant, call it capital A, over s, plus some other constant, call it capital B, over s plus 3. Can I find constants a and b where those are equal? Turns out you can. How do you solve for it? Multiply both sides of setting this equal to this by this common denominator, s times s plus 3. I'm ignoring the e to the negative 5s for the moment. That'll give me 1 equals, because s times s plus 3 cancels there, a times s plus 3, because the s's cancel for the first term, plus b times s, because the s plus 3's cancel with the second. Technically speaking, to be a bit more rigorous, I should expand this out as a linear function, something times s plus a constant, set the coefficient of s equal to 0, because there is no s on the left side, and the constant term equal to 1. However, it's quicker, and it does work, if you just pick special values for s, like s equals 0 to make that term go away, and s equals negative 3 to make this term go away. If s is 0, I get 1 equals a times 3 plus b times 0, and therefore a must be 1/3. And if s equals negative 3, I want this equation to be true no matter what s is, I'll get 1 equals a times 0 plus b times negative 3, and so b becomes negative 1/3. Okay, so I'm going to use that here as well as linearity. I can in fact write, based on what I've just done, and this thing I'm trying to find, I can bring the 1/3s out in front essentially. 1/3 inverse Laplace transform of e to the negative 5s times 1 over s. The e to the negative 5s needs to stay in there, it's not a constant. Minus 1/3, because b is minus 1/3, inverse Laplace transform of e to the negative 5s times 1 over s plus 3. Now those expressions inside the inverse Laplace transform are a bit simpler. This is where I now want to use this fact. So I want to use it in reverse. A, in both cases, here and here, is 5. It matches the a right there. So u5t, when I go backwards, is going to become involved. That shouldn't be surprising, because the original right-hand side was u5t. Just be careful. 2e to the negative 3t plus 1/3. How do I use this now? What is a again? A is 5. I'm comparing these things here. What is capital F of s? Well, for this one, it's 1 over s. I know this fact. That's going to be relevant. So I'm going to get this expression, u5t times little f of t minus 5, where little f of t, for this one, is 1, a constant function. Plugging in t minus a doesn't matter. That's just 1. It will be a little trickier for the next one. This is a minus 1/3. Again, the a is 5, u5t. Now I'm looking at this 1 over s plus 3. That's playing the role of the capital F of s. What's little f of t? I need this fact here, with this a equal to -3, not 5 like it was there. So the a is playing two different roles here. That a equals -3. So I'm going to get e to the -3, not times t, this is the final tricky thing, but instead times t minus a, where this a comes from that a, which is same as this a, which is 5. Oh boy. Wow, that's kind of confusing. Okay. Check it out. Compare, going backwards, in fact, you'll see this works. And I don't have to have the times 1 here, but this is effectively the answer. I also could expand the -3 through the parentheses there. I also could, out of these two terms, factor out a 1/3 and a u5t. It doesn't matter. This is good enough for the final answer. The second problem is a theoretical problem about unstable equilibrium points. It's really a proof. If you don't care about that kind of problem, I do have chapters. You could skip ahead to some other chapter, again, for example, about Hamiltonian systems or nonlinear systems or something like that. We've got the following linear system. Let me quickly draw the phase portrait of this. It's a linear system, and pretty clearly, the origin is the only equilibrium point. In the x direction, it's stable. dx dt is -x. You're going to have arrows that point toward the origin in the x direction. By the way, the corresponding matrix for this linear system is going to be diagonal, -1, 0, 0, 1. The eigenvalues are going to be plus or minus 1. -1 is an eigenvalue, and the eigenvectors for that are horizontal. And dy dt is y. In the vertical direction, you're going to have straight line solutions going away from the equilibrium point. Ultimately, though, you've got one positive, one negative eigenvalue. This equilibrium point at the origin is a saddle point. That's the basic picture. The flow of this system is this formula. What is a flow? Well, essentially, it's the solution, the general solution. You want to think, when you think about flows, you want to think of this expression for any fixed value of t as telling you where you map the initial condition x comma y, or this column vector xy to after t units of time. That's how you want to think of it. Of course, to be a true solution, you want to think of x and y as fixed and t as the variable, but it's also helpful to imagine t is fixed and asking what the point xy gets mapped to after t units of time. Use the definition of what it means to be an unstable equilibrium point to finish a certain argument that I start here. For y, the origin, the unique equilibrium point at the origin, is an unstable equilibrium point. Okay, you gotta know what stability and instability means. Let me just focus on instability. Instability means, in this picture, there's some disk centered at the equilibrium point at the origin. How big is the disk? That's not clear. Of radius, typically called epsilon, so that no matter how small of another disk you consider, it could be really tiny, of radius, call it delta, there's at least one point, maybe more, inside this disk centered at the origin of radius delta that eventually goes outside the other disk of radius epsilon when t is large enough. Say that again. To be unstable means there's some disk of radius epsilon. It's not clear what epsilon is. Here, evidently, epsilon equals 1 will work. And in fact, any epsilon that's positive can be made to work in this problem. But it's good enough to find some disk of radius epsilon so that any other disk of radius delta, no matter how small delta is, has at least one point, maybe more, that travels out of the bigger disk for large enough values of time. So epsilon is, I'm taking to be 1, and delta is taken to be given. I'm choosing this point. Notice that point, when delta is positive, is on the positive y-axis somewhere. And in fact, if this picture is accurate and this radius is delta, then it's going to be half as close to the origin there. It's going to be right about there that I'm picking this point. It's on the y-axis above the origin. You can see from the picture it's eventually going to go far enough to away from the origin that it'll be farther than epsilon equals 1. The question is, how far do you need to go? So you need to do a little scratch work. Do, by the way, notice that the distance between y, this point right here, and y0, which is the origin, is, by the Pythagorean theorem, this square root, which ultimately equals delta over 2. Delta is positive here, so this square root becomes that. I'm wondering, how big does t need to be to make, let me go ahead and replace y0 with 0, 0, to make this greater than or equal to epsilon, which is 1? Can I find t large enough to make that happen? And the answer is yes, you will be able to. What is phi superscript t of y? Well, there it is right there. But I am plugging in this particular vector y right there. So its x-coordinate is 0, its y-coordinate is delta over 2. When I use this formula, the first component still stays to be 0 because x is 0. The second component becomes delta over 2 times e to the t, because I replace y with delta over 2. Subtracting 0, 0 doesn't affect things. Again, there's still scratch work here. What is this norm? What is the magnitude of this vector? Its distance to the origin. It is delta over 2 times e to the t, because the first component is 0. So the distance to the origin is the same as the second component. Can I choose t so large to make that happen? It's a matter of solving for t. Multiply both sides by 2 over delta. Delta is positive, so the inequality doesn't change direction. Then take the natural log of both sides. These are two-way implications here. Natural log is an increasing function. Natural log of e to the t is t, and that's got to be greater than or equal to natural log of 2 over delta. And that effectively, based on your scratch work, is how big t needs to be. But now we need to say it in the reverse order. That's the logic that needs to be set in. So I've started it, chosen this point. The distance between this point and the origin is this. Now choose, so I'm starting the rest of the proof. T greater than or equal to what my scratch work found, natural log of 2 over delta. Okay? As long as t is greater than or equal to that, I'm going to be able to reverse my scratch work and ultimately show that this is true, and that's what I want to show is true. Technically, proof should be written in sentences. I'm going to exponentiate both sides. You can say e to the t is greater than or equal to e to this thing, which is 2 over delta. E to the t is also an increasing function, so the inequality doesn't change direction. And multiply both sides by delta over 2. Delta over 2 times e to the t is greater than or equal to 1, which is the epsilon. Now say this fact, but the distance between the flow evaluated at y minus y0, the distance between that flow point and the origin, is equal to the magnitude of the vector 0 delta over 2 e to the t, which is delta over 2 e to the t, which I've just shown is greater than or equal to epsilon. That means we're done. QED. We have shown what we wanted to show. We wanted to show there's a large enough value of t that's going to map this point outside of the bigger disk of radius epsilon. How big does t need to be? It needs to be bigger than the natural log of 2 over delta. Okay? All right. On to the next problem. The next problem is about trapping regions. The system is kind of complicated looking, a complicated looking nonlinear system. Don't be scared. Okay, this problem is not as hard as it looks. It is worthwhile, and I teach my students about this, to think of this in terms of polar coordinates as well. That's something they should know. In particular, the square roots of x squared plus y squared here can be replaced by the polar coordinate r. That's a helpful thing to do in this problem. I didn't make a picture of what the phase portrait looks like, but let me just quickly tell you without proving it. The phase portrait in the xy plane is going to have an equilibrium point at the origin. It's also going to have the unit circle as a solution that comes back to itself as a periodic solution, and other solutions are going to go toward it. All other solutions, except for the origin, go toward the unit circle as t gets larger. That's what the picture looks like. It turns out you can use technology to confirm that if you want. Look at the directions now. It's not as hard as it seems. Let R be the annulus or ring shape centered at the origin, whose inner radius is a half and whose outer radius is 3/2. Here's the official definition of R. So if the purple circle there is a radius 1, a radius 1/2 circle is going to be about like this, and a radius 3/2 circle is going to be about like this. R is this annual, this is the official name of this shape here, ring shape. In the polar coordinate R equals square root of x squared plus y squared, you can say it's determined by this condition. R is between 1/2 and 3/2 like I drew here. This is a 3/2 right there. I do teach my students how to do these kind of problems in lectures that I make. We claim that R is a trapping region for the system above. And what that means is solutions that go into it never go out. And that can be verified by effectively showing that the vector field for the system always points inward along the boundary, like I'm trying to draw here, inward along that boundary and inward along the inner boundary as well. We're going to partially verify that by following these directions, showing that the dot product n of y dot f of y is always negative, where f of y is the vector field and n of y is this vector, is an outward pointing normal vector along the outer boundary of R. So for an arbitrary point here along the outer boundary, call it, say it's right there, the vector field is going to be f of y, and n of y is going to turn out to look like this. It is an outward pointing vector that is also normal to the curve there. It's perpendicular to it, it turns out, and that's based on the fact that it's pointing directly away from the origin, and this is a circle centered at the origin. You can see visually it looks like the angle between those two vectors is bigger than 90 degrees, so their dot product should be negative. Okay? I do that at an arbitrary point, and that'll verify that the dot product's negative everywhere, and that'll verify the vector field is pointing in along the outer boundary. To fully verify its trapping region, we'd also have to verify it's pointing inward along the inner boundary. And we want to take an inward pointing normal vector. So it's just a matter of computing this dot product. Right there, using n of y, which has components x, y, and the vector field, which has these components, x minus 2y minus x times r, where r is the polar coordinate, and 2x plus y minus y times r. Take that dot product. You get x times this thing is x squared minus 2xy minus x squared r, and then plus y times this thing plus 2xy plus y squared minus y squared times r. And simplify. These two things cancel. X squared plus y squared, those two terms can be put together. That's the same as r squared. And with the other two terms here and here, I can write minus in parentheses x squared plus y squared times r. And that's the same as r squared as well. So this becomes r squared minus r cubed in the polar coordinate r, which is also r squared times in parentheses 1 minus r. And now you just need to think, do a little explanation. Where r on the outer boundary, where r is 3/2, it's not really much explanation. You can just say when r is 3/2 along that outer boundary, r is the constant 3/2. This thing is a positive times a negative. It's negative. It's 3/2 squared times 1 minus 3/2. That is negative. That's enough to say that, but if you want to figure out what this number is, it looks like it's negative 9/8. The important thing is it's negative, and it's constant. It doesn't matter what point along the outer boundary we are at. That dot product will be negative. The angle between these vectors will always be bigger than 90 degrees, and that's enough to verify the vector field is pointing inward along that outer boundary. Part B, the only equilibrium point is the origin. Only equilibrium point. Assuming R is indeed a trapping region, so you verify that it's pointing inward along the inner boundary as well, what theorem now guarantees the existence of a periodic solution inside of R? Now, I'm only requiring my students to just say the name of the theorem, and it's called the Poincare-Bendixson Theorem. But let me just verbally say what it says. It says if you've got a two-dimensional system, a planar system of two first-order differential equations, with a phase portrait that can be drawn in the plane, and you've got some trapping region. And if there are no equilibrium points inside that trapping region, which there are not in this green region, the origin is not in the green region. It's inside of both circles, but it's not in the annulus. It's not in the inside of the annulus. There's no equilibrium points in there, and it's a trapping region. There's got to be a periodic solution in there. That's what the Poincare-Bendixson Theorem says, okay? Got to be at least one periodic solution. There could be more than one, actually, but there's got to be at least one. But that's the name of the theorem. Number 4. Let g of x be this multivariable calculus function, a real valued function of two variables. Use the chain rule to verify that its opposite, negative g of x, is what's called a Lyapunov function for the gradient system that you see here. To be a gradient system means that this right-hand side is the partial derivative of g with respect to x, and if you check it, it does work. 2x plus 3y plus 0 is the partial derivative of g with respect to x. And the second right-hand side for dy dt is the partial of g with respect to y, and you can double check that. Differentiate this with respect to y, get 3x plus 12y squared. That's what makes this a gradient system. The vector field is the gradient of some function. This function g, it's called a potential function, and that's related to potential energy in physics. But we want to show its opposite is what's called the Lyapunov function. We want to verify that this derivative is always less than or equal to 0. To do that involves the multivariable calculus chain rule. In this context, it would say, take the partial derivative of this function, negative g, with respect to x first, and then multiply that times dx dt, and then add the partial derivative of this function, negative g, with respect to y, times the derivative of y with respect to t. I am assuming this thing is a solution. Therefore, dx dt and dy dt are given by the differential equations. I don't actually even have to use the formulas that you see here. I can just replace dx dt with the partial of g with respect to x, and dy dt with the partial of g with respect to y. You don't see any t's anymore. Where are the t's? Well, they're in there. I'm just not writing them. These things all ultimately depend on t along the solution curve. But it doesn't matter. This is now the opposite of, in parentheses, the partial of g with respect to x squared plus the partial of g with respect to y squared. We're only dealing with real quantities here. This thing is always greater than or equal to 0. Therefore, because of the minus sign, the entire thing is always less than or equal to 0 for all t. Okay? I can do this without knowing formulas for these solutions. Okay? There is some formula that maybe cannot be written in terms of elementary functions for x of t and y of t. I am differentiating along that solution curve. Ultimately, everything does depend on t. I should say this is true for all t. That's enough to verify this for all t. And that's enough to verify that it's a Lyapunov function. Technically, there's a technicality that you really also want it to be strictly less than 0, except at a discrete set of times, but we're not going to worry about that here. The next problem is about Hamiltonian system. This system right here is a Hamiltonian system. Part A says, quickly verify it's Hamiltonian. If you know how to do this, it'll take you 15 seconds. Okay, well, let me explain a little bit, so it'll take me longer than 15 seconds. Let's call this right-hand side function f of xy, and this right-hand side function g of xy. This is a Hamiltonian system exactly when this right-hand side is the partial derivative of some function, call it h, with respect to y, and this right-hand side function is the opposite of the partial derivative of that same function with respect to x. Now, if that's the case, by something called Clairaut's theorem, if I differentiate this function with respect to x, it should be, because of the negative sign there, the opposite of the derivative of this function with respect to y. And that is the quick verification that turns out to be good enough to verify this is a Hamiltonian system. Find the partial derivative of y of f with respect to x, and see if it equals the opposite of the partial derivative of g with respect to y. Clairaut's theorem is the equality of mixed partial derivatives in nice situations. That's what we're ultimately using. The partial of this first function with respect to x is 2y. The opposite of the partial of the second function with respect to y is the opposite of, differentiate this with respect to y and get negative 2y, which equals 2y, and these are the same functions. They're equal no matter what x and y are, and that turns out to be enough to verify, yes, this system is Hamiltonian. There is some function h where this is true. Part B says to find a Hamiltonian function, find h. The answer is actually not unique, because we're going to integrate to find h, and ultimately there's an additive constant that can be anything that will ultimately mean h is not unique. You could approach it by either first integrating this expression with respect to y or this one with respect to x and then negating it. Let's do this one with respect to y first. The h function can be written as the integral of the f function with respect to y. So it's integral of 2xy plus y squared with respect to y. Treat x as a constant. You're going to get x times y squared when you integrate this one, plus 1/3 y cubed when you integrate that one, plus some integration constant, which is really not a constant. It really could depend on x, because in the end, h can depend on x, and it does right there, in fact. I'll call that phi of x, some function of x. I know h has to have this form. To figure out what phi of x is, I need to satisfy the other condition, that this is true. Find the opposite of the derivative of h with respect to x. That'll be the opposite of differentiate with respect to x. Here you get y squared, and here you get 0, and here you get phi prime of x. Distribute the minus sign through, that's minus y squared minus phi prime of x. I need to set this equal to x squared minus y squared. Set that equal to x squared minus y squared. The y squareds are already equal. This implies that phi prime of x equals negative x squared. So I can take phi of x to be negative 1/3 x cubed plus c. But you might as well take the c to be 0. So if I've not made a mistake, I'll try to put notes on the video if I did make a mistake. Looks like h of xy is this expression, and then substitute that in there for the phi of x. So it looks like it's xy squared plus 1/3 y cubed minus 1/3 x cubed. Of course, I can double check it quick, see if it matches up here. Partial of this with respect to x is y squared. Excuse me, with respect to y is what I need to do first. The right-hand side up there is 2xy. That differentiates to 0. This differentiates to y squared. 2xy plus y squared matches that. Derivative with respect to x, and then negate. Well, the derivative with respect to x is going to be y squared minus x squared. Negate that, you do get x squared minus y squared. It is working. It is right. That's part B. C, verify your solution function is constant along solution curves by showing its derivative along the solution curve is always equal to 0. This is very much like the gradient problem. And in fact, once again, we can do it in the general setting. The derivative of h along the solution curve, we don't need the formula for the solution curve here. I need the chain rule, is the partial of h with respect to x times dx dt plus the partial of h with respect to y times dy dt. And yeah, I can use this particular function and plug in that function, but I also can use the fact that I know it's Hamiltonian. I know dx dt is equal to dh dy, and dy dt equals negative dh dx. So this becomes dh dx times dh dy. Sorry, that's an h there. Plus dh dy times negative dh dx. And sorry, you couldn't see it. These end up canceling. And again, there's t's in the background. I'm not bothering to write them. Everything along a solution curve does depend on t, but it doesn't matter. This is identically equals to 0 for all t. So it doesn't matter. You don't need the actual formulas for the solutions. Part D, the level curves of the Hamiltonian function are found in Part B are shown in this picture where h is constant along these curves. That's what level curves mean. Use this picture to help you sketch the phase portrait. Note the only equilibrium point is the origin. Be careful about directions. Okay, here's the key thing. H is constant along solution curves. These are the level curves where h is constant. Therefore, these things are solution curves. The only trick is to get the direction of the arrows correct as t increases. And that can be easily done by picking points. And it's probably simplest just to pick one point and then make it consistent everywhere else. And the one point we could pick, for example, is some point in the first quadrant where x and y are both positive. Say the point 1, 1. Should I use that point and say right about here? Actually, all that's needed is to think about the sign of dx dt there. When x is 1 and y is 1, dx dt is positive. Turns out dy dt is 0. It turns out at 1, 1 we are at a point where the tangent is horizontal. I didn't draw it perfectly that way. In fact, this curve is not necessarily on the point 1, 1. But ultimately, dx dt is positive here, so we're going to have rightward pointing arrows. The level curves themselves are solution curves. And this stays consistent as you sort of go around the horn. You could double check this by figuring out dx dt and dy dt for other points, and you would get consistency here. Drawing the arrows on top of these solutions emphasizes that on top of these curves emphasizes that they are in fact solutions. Yeah, there we go. All right. If you want to double check other directions, that's fine. This does work. Not a very typical equilibrium point there. It's not a hyperbolic equilibrium point. If you linearize near the origin here, I believe the Jacobian matrix is probably going to have zeros in eigenvalue. That's my guess. So the Hartman-Grobman theorem for linearization would not apply, and so we could not use it. And a strange stuff is happening at that equilibrium point. It's some sort of weird saddle point, right? That's a pretty weird looking saddle point, not typical. Number 6. Consider the same second order. Ignore the same because it's referring back to some other problem that's actually not on this this practice exam. Consider the second order initial value problem that you see right here. Second order differential equation can be solved without a Laplace transform, but it also can be solved with a Laplace transform. Solving it with a Laplace transform is pretty challenging, but it can be done. I'm helping my students save time by telling them steps, and they're just needing to verify some things. To fully do this from scratch can take a really, really long time. Part A says you show steps using the linearity of L. We did that in the very first problem. And this fact and this fact. I used that in the first problem for the first order equation we had there. I have not used this fact yet. Also, we're going to use the fact that this is true to verify this. The Laplace transform of cosine of 2t is this, s over s squared plus 4. So telling them a bunch of things to use. Linearity first is going to imply that if I take the Laplace transform of the left-hand side, I get L of y double prime plus 4L of y prime plus 13L of y. That's linearity. L of cosine of t is what you have to compute on the right-hand side. It equals what you see here, s over s squared plus 4. Now use these two properties and use the initial conditions, which are both 0, makes things a little simpler. So this becomes s squared L of y minus s times 0 minus 0 plus 4s L of y minus 0 plus 13 L of y equals s over s squared plus 4. You can factor out an L of y here, like this. And your last step for part A is just to divide both sides by s squared plus 4s plus 13, which you know you have to do, because what do you see there? Let's just write a 3 dots for therefore. Therefore, L of y is s over the product of s squared plus 4 and s squared plus 4s plus 13. That's doing part A. That's verifying this fact. Now, just like in problem 1, to find the solution, you'd have to find the inverse Laplace transform of that. Yikes. It's not a sum or a difference. I can't use linearity yet. So what do? I'm telling them that using partial fractions, it can be shown that this fraction can be written as this combination. You do not need to show that. It takes a fair amount of time. Part of what's the partial fractions is more complicated in this situation because the s squared plus 4 and the s squared plus 4s plus 13 in the denominators cannot be factored over the real numbers. The roots are complex. They're irreducible. And because of that, you need linear terms up top that could involve an s, not like a number 1 where they're just constant. So you're just trusting me on this. Furthermore, it's good to note that this is true and that we can write this expression you see here in this way. How do I go from there to there? Some tricky algebra. For example, the 9 over 145 times s over s squared plus 4 comes from this 9s over s squared plus 4 times 1 over 145. Well, what about the 16 over s squared plus 4 times 1 over 145? That comes into play right there, because 8 times 2 is 16. But why do I write it like that? Why do I have an 8 there and a 2 there instead of just a 16? It's because it helps you solve the problem. With this term, the s squared plus 4s plus 13 is written by completing the square like this, s plus 2 quantity squared plus 9, like you see in those two spots. And having a 9 and an s plus 2 up there and a 34 and a 3 there is once again the result of some tricky algebra, essentially replacing the s here by s plus 2 and then compensating by subtracting an 18, I think. 34 times 3, yeah, something like that. You can double, I think I better not take the time to do it. You can double check that if you like. Now here's what you need to do. Part B. Find these 4 inverse Laplace transforms using the facts about Laplace transforms, including something called the shifting the origin on the s-axis property, which we'll need for 3 and 4. So let's write down what is the shifting on the origin on the s-axis property. I haven't mentioned that property yet. It says that the Laplace transform, it turns out, of e to the at times f of t equals capital F of s minus a, where capital F of s is the Laplace transform of little f of t. And number 1, we have the shifting the origin on the t-axis property, which was that the Laplace transform of u sub a of t times little f of t minus a was e to the negative as times capital F of s. This is a little different, but still true. It's going to be relevant for these two, evidently. How? Well, the s plus 2 that you see in both spots is going to play the role of s minus a. So a is going to end up being negative 2, and you're going to get factors of e to the negative 2t out when you do the inverse Laplace transform. The other ones, 1 and 2, are memorized. Inverse Laplace transform of s over s squared plus 4, actually that's there, is cos 2t. Inverse Laplace transform of this one, 2 over s squared plus 4. Since 4 is 2 squared, it turns out, is sine of 2t. The general facts that are related to these particular facts is that the Laplace transform of cosine of omega times t is s over s squared plus omega squared. Omega looks like a w. And the Laplace transform of sine of omega t turns out to be omega over s squared plus omega squared. Okay? Facts that can be derived. So that's 1 and 2. What about 3 and 4? Inverse Laplace transform of this. S plus 2 over s plus 2 quantity squared plus 9. Notice that 9 is 3 squared. If I replace the s plus 2's here and here with just s, it would be like this one, and I get cosine of 3t, because 9 is 3 squared. But I've got s plus 2's there. I also have to use this fact. I'm going to get, using this fact, with a equal to negative 2, e to the negative 2t times cosine of 3t. The little f of t is the cos 3t. The e to the at is this, where a is negative 2, because I've got s plus 2's there and there, matching s minus a when a is negative 2. 4 is similar. Inverse Laplace transform of that. 3 over s plus 2 quantity squared plus 9. If that were just an s instead of an s plus 2, this would be sine of 3t. But it is an s plus 2, and therefore I also need a factor of e to the at, where a is negative 2 again, times the sine of 3t. So I have now finished part B. Part C. Use these facts from part B to find y, the unique solution of the IVP. We also need this thing here as being a way to write the Laplace transform of y. Y, for part C, y is the inverse Laplace transform of this thing, which means it's also the inverse Laplace transform of this thing. That's a linear combination. Inverse Laplace transform is linear. We're going to get the same linear combination with these coefficients of these inverse Laplace transforms. So y is going to be 9 over 145 times cosine of 2t plus 8 over 145 times sine of 2t minus 9 over 145 times e to the negative 2t cos 3t finally minus 34 over 435 times the inverse Laplace transform of this, which is e to the negative 2t sine 3t. And there, as if by magic, is the solution of the initial value problem. Solving that without Laplace transforms can be done and is probably in the end easier, especially if you had to do all this work that I gave my students. You can use what's called complexification and guessing, finding a solution of the corresponding homogeneous equation, a general solution, and a particular solution of the what's called a complexified equation, which you end up using Euler's identity, complex numbers, and that kind of stuff. I did that in a previous video. I'm not going to do it now. 2 pages left. The last page is quick. It's multiple choice and true false. This one still takes a little while. One parameter family of nonlinear systems. A is the parameter. It's one system for each value of A. We're considering infinitely many systems of nonlinear differential equations here as A varies. For any fixed value of A, you think of A as a constant and you could draw a phase plane, phase portrait. But you're interested in, well, how does that phase portrait change as I consider new systems for new values of A? Part A says, show algebra work to verify that the origin is the equilibrium point and also these 2 points are equilibrium points. And because A minus 1 is 0 when A is 1, a bifurcation in the number of equilibrium points occurs at A equals 1. technically speaking, you could just plug these numbers into the right-hand side functions, fxy and g of xy, and confirm that you get 0 in both cases. That's technically a more rigorous way to do it, but I'm fine with my students, as we usually do, setting up a system of equations to solve for the equilibrium points. I want to set the right-hand side functions both equal to 0. This is a nonlinear system of algebra equations. This one implies y equals x, and then you can plug that into this one to get x minus ax plus x cubed equals 0. Factor out an x and get x times, in parentheses, write it as, say, x squared plus 1 minus a equals 0, which gives x equals 0 as one solution here for this one, and also x squared equals a minus 1, so that x equals plus or minus square root of a minus 1. Using the fact that y equals x at equilibrium points gives 3 equilibrium points. When x is 0, y must be 0. When x is square root of a minus 1, y must be square root of a minus 1. And when x is negative square root of a minus 1, so must y be negative square root of a minus 1. Okay, so that's part A. Part B, find the general Jacobian matrix. There's what it is. Take those partial derivatives, j sub a of xy. Look at f and g. Derivative of f with respect to x is 3x squared minus a. That goes in the upper left entry, 3x squared minus a. It's representing that partial derivative. What's the partial of f with respect to y? Look back up here, it's 1. That goes in the upper right entry. Partial of g with respect to x is in the lower left. That's negative 1. And partial of g with respect to y is in the lower right. That's positive 1. That's part B. That's the general Jacobian matrix. Part C, the equilibrium point at the origin is one type of equilibrium point when a is less than negative 3, another type when a is between negative 3 and 1, and another type when a is bigger than 1. Use the trace and determinant of the Jacobian matrix to classify these types. And I'm really using linearization, officially the Hartman-Grobman theorem. I'm plugging in the origin at an arbitrary value of a. I get negative a, 1, negative 1, 1. The trace of that depends on a is the sum of the things on the main diagonal. It's negative a plus 1, or if you prefer 1 minus a. And the determinant also depends on a is negative a times 1 minus 1 times negative 1 is negative 1. It gives me the same thing. Okay, they happen to be the same thing here. That was not guaranteed to happen, but it did happen here. How do I use this to classify the equilibrium point at the origin for different values of a? You need something called the trace-determinant plane, which is not a phase plane. I'm not drawing solution curves when I draw the entire t-axis, the positive d-axis, and a parabola whose equation is d equals t squared over 4, or equivalently t squared equals 4d. Those are called critical loci in the trace-determinant plane, and it's when the parametric curve defined by these equations crosses one of these curves that bifurcations occur, the nature of the equilibrium point at the origin changes. If you graph this system of parametric equations, you're going to get, it's going to be on the line y equals x. It's going to start up here when a is a large negative number and go down toward the origin. Both t and d decrease as a increases, and go like that. And you're going to have bifurcation values of a right here and here, which evidently are at a equals negative 3 and a equals positive 1. You can double check that. Certainly when a is positive 1, we're at the origin. 0, 0. When a is negative 3, these both become 4. A is negative 3 makes us at the point 4, 4, and 4, 4 is on that parabola. It is on the repeated root parabola. So what this means is that, knowing the trace-determinant plane, when a is less than negative 3, this point is up here, and that means it's what's called a spiral, a real source. A is less than negative 3. It's a real source, non-spiral source. When a is between negative 3 and 1, when we're in here, it's a spiral source, it turns out. complex eigenvalues with positive real part. And when a is bigger than 1, that's when we're down here. That's where it's a saddle point. Okay? And there's your classification. Part D, another equilibrium point. This one is one type when a is between 1 and 3, and another type when a is bigger than 3. Once again, use the trace and determinant to classify those types. That is part D. I'll put it over here. J sub a of square root of a minus 1 comma square root of a minus 1. Replace x with square root of a minus 1. Got to square it, so you get 3 times a minus 1 minus a. Simplify. 3a minus a is 2a, and then we get a minus 3. So the trace, sum of these two things is 2a minus 2, 2a minus 3 plus 1, and the determinant also depends on a. It's 2a minus 3 minus negative 1, and once again, we got lucky, and the trace and determinant are equal, and that just makes it a little easier because it makes it so in the trace determinant plane you're on the line. I said y equals x before, but it's really d equals t. In the trace determinant plane, when a is 1, both of these have a value of 0, you're at the origin. When as a increases, both of these increase, you're going to be going up and to the right, and you're going to cross the repeated parabola at some other point. Evidently, you're here when a is 1, and here, based on the directions, when a is 3. And so you travel from being a spiral source when a is between 1 and 3, spiral source, to being a non-spiral source when a is bigger than 3, a real source. Okay? Last part, E. And then we're on to the multiple choice and true false. We're almost done. Sketch the phase plane when a is 2. So when a is 2, what does the system become? A is 2. What does the system become? Look back up here, replace the a with 2. dx dt is y minus 2x plus x cubed. dy dt is still y minus x. We can use these to draw null lines where dx dt and dy dt are 0. Now I'm drawing a phase plane, a phase portrait xy plane, not TD anymore. X null line, I'll make green. If I set this equal to 0 and solve for y as a function of x, I get y is negative x cubed plus 2x. If you graph that with technology, say, it's going to look about like this. It's the x null line. That's where solutions cross with dx dt equal to 0, meaning with 0 x component. Got to cross vertically there. And the y null line is where dy dt is 0. And that's going to occur along the line of y equals x. Will it be like this or like that? I'm not sure. I'm not going to worry about it. Say like this. Let's just pretend that's right. That you cross horizontally. dy dt is 0. Yeah, I'm pretty sure that's right. Equilibrium points are where the distinct null lines cross. Here, here, and here. We are in the case where a is 2, where the origin is a spiral source. And this point is a spiral source as well. Let's see. No, origin is not a spiral source. It's a saddle point. Saddle point at the origin, spiral source at this point. Also turns out spiral source at its symmetric point across the origin, because if you put minus signs in front of these, it wouldn't affect things because we're squaring it. So spiral sources here and here, and a saddle point there. You need to check the signs of dx dt in the different regions. When we're above this cubic, this will be positive. dx dt will be positive above the cubic. including down in there, and negative when you're below the cubic, including in here. dy dt will be positive when you're above the line y equals x, including in here, and negative when you're below the red line, the y equals x. You know this is going to be a spiral source. Start with an initial condition near it. You know you're going to have to sort of wind around and cross these null lines correctly. Something about like this, say. Similar thing's going to happen over here. Spiral source. It's tricky. This takes practice. There's going to be something called the separatrix solution that spirals away here, but doesn't come back to going here like that or like this, but instead heads straight toward this equilibrium point at the origin. I shouldn't say straight, along a curve. Another one over here will do the same thing in the opposite side. This is symmetric here, a symmetric kind of system. Those are called separatrices. There are also going to be separatrices that are in the unstable direction for the origin that would have to look like this and probably go ultimately like that and ultimately like this, etc. You can draw in some other solutions. There'll be one, for example, that goes like this, say. Another one that goes like this, say. This is decent. It's not a perfect drawing. Nobody can draw a perfect drawing. Other solutions will go close to this equilibrium at the point of the origin without approaching it. Okay, it's a pretty decent drawing, I think. Probably enough to give myself full credit here. Pretty decent. All right, last page. True, false, and multiple choice. True or false? An equilibrium point for a two-dimensional system that is a center is stable. Centers in the plane have phase portraits that might look like this, with solutions going counterclockwise, or they could be going clockwise. What does it mean to be stable? It means if you if you start, excuse me, if you start sufficiently close to the equilibrium point, you're not going to go too far away. That's a very, very loose way of describing it. And yeah, no matter if you start really close to the equilibrium point, you're not going to go too far away along the solution curves because they're ovals near the equilibrium point. It is stable. This is true. Unstable would include things like saddle points or sources. You start near the equilibrium point, but you're not on it. Well, for a source, you're all for sure going to go away from it, far away. And for a saddle, certain solutions will go far away from it. It's related to the unstable proof from problem number 2. It's not asymptotically stable. If I said it was asymptotically stable, the answer would be false. Asymptotically stable means not only do solutions not go too far away, they in fact approach the equilibrium point as t increases. That is what happens with sinks. But centers, while they're not asymptotically stable, are stable. The answer is true. Number 9, which of the following choices best describes the concept of a hyperbolic equilibrium point? The definition of a hyperbolic equilibrium point is that when you calculate the Jacobian matrix for the system evaluated at the equilibrium point, no eigenvalue has zero real part. If they're real eigenvalues, they're non-zero. If they're complex eigenvalues, they're not purely imaginary. And what that ends up meaning related to these things is that it's actually typical, not a place where a bifurcation occurs. It's not because solutions look like hyperbolas. It's not that it's the same as a stable equilibrium point. Stability does correspond to essentially observable, asymptotically stable especially, but it's not the same as stable. It's also not the same as unstable. It means it's typical. When your eigenvalues, when one eigenvalue crosses really the imaginary axis in the complex plane, whether it's through the origin or on the imaginary axis, not at the origin, that is when bifurcations occur. The nature of the eigenvalues change. But that's not typical. Typical is when they're not. No bifurcation is occurring. Part C is about something called sensitive dependence on initial conditions. Your teacher may or may not have talked about that, but that's equivalent to the butterfly effect, which says arbitrarily small changes in initial conditions can drastically affect long-term behaviors. The butterfly effect says if a butterfly flaps its wings in California one day, it's going to cause long-term effects in the weather, say in New York, okay? Maybe it would change what happens with the weather in New York, say 2 weeks later or something. That's the idea of chaos or sensitive dependence on initial conditions. Arbitrarily small changes to initial conditions can lead to drastically different long-term behaviors. Emphasis on long-term. It would not lead to drastically different short-term behaviors. Last problem. A really, really basic partial differential equation problem. Here's a function of two variables, t and x. Which partial differential equation, PDE, which is, these are all heat equations, does it solve? It evidently solves one of these. I need to find the partial derivative of this with respect to u, and the second order partial with respect to x twice, and see if there's what value of k will make them equal to each other as functions of t and x. Partial derivative with respect to t treats the x as constant, so cos 3x is constant. I get an extra factor of -2 from the chain rule. There's the partial derivative of u with respect to t. For the first order partial with respect to x, treat the t as constant. The e to the -2t just stays there. Derivative of cos 3x with respect to x will be negative sine 3x times 3. Simplify a little bit. This is -3 e to the -2t sine 3x. And therefore, the second order partial of u with respect to x twice, I differentiate this with respect to x. I get another factor of 3, and the negative sign stays as is. So I'm going to ultimately get -9 e to the -2t, and the sign turns into a cosine. These two things are pretty similar to each other. They will match if the k that goes in front of here is chosen so that k times -9 is -2. In other words, k is 2 ninths. Right? 2 ninths times -9. The 9's will cancel, giving you -2. Matches the -2 there. The e to the -2t and the cos 3x both match already. So if I've not made a mistake, it looks like the answer is B. Again, I put notes if I do make mistakes. Thanks for watching.